All right, so I'm going to go over the recitation relay. We did a relay in my ochem 2 class this week for recitation, and this is on aldehydes, ketones, and a little bit on carboxylic acids. Not a ton though. Here's the rules, just for if anyone's curious, but I'm going to go ahead and start with just making the video key for my ochem 2 class for this semester, fall 2024. So when we have HCN and KCN, it can go either way. If you just had HCN, it could be acid protonated, but there's excess CN minus because of this K plus. So the CN minus is likely to attack first, and you would get a O minus with your R group, whatever R groups were already there, and your CN. And then this would be protonated. Probably either the H from the HCN, there'd be excess, just enough of the H plus that you can use the acid there, or you can add acid if there's a little bit of excess of the KCN. And you would get a cyanohydrin. So CNOH. I rearranged those. It doesn't super matter how those add in, but this would be, you would really get a racemic mixture of this because this is flat and you can get attacked from either side. So the final product of this is a cyanohydrin. Okay, dissolving benzaldehyde in methyl alcohol, especially in the presence of acid, would establish an equilibrium with what compound? So you don't have to draw the mechanism out for this to get the answer, but I think it's easier if you do. So if you have this in acidic conditions, the first thing that's going to happen is OH plus. And that first step is a protonation. Usually when you have methyl alcohol or any kind of alcohol with an aldehyde or ketone, it's usually in acidic conditions. And you get OH. So that was already protonated. And then the alcohol added OH. This is positively charged, and CH3 from the methyl alcohol. So you end up with this. This is a hemiacetal, or if it's a ketone, a hemiacetal. And if you deprotonate it, that would be the hemiacetal. Right now it's a protonated hemiacetal. But a lot of times, just instead of doing a deprotonation and a reprotonation, I do a proton transfer because it's easier for students to see. It's not technically the best way, but it's easy to see. And then you get OCH3. So this has now become a good leaving group. And after that becomes a good leaving group, your carbonyl, so to speak, can be restored and your leaving group will be kicked out, and you get this very weird looking structure. Oh, this is a hydrogen, it's an aldehyde, where this is positively charged. As you can guess, that is not the most stable, and it is in resonance with another structure that has the lone pair up here, and this being positively charged. So another one of your acids would attack, and this bond would break, and you would get OCH3 with your H, and it's positively charged, and on the other side your O with a CH3 bonded there. And then you'd get a deprotonation step if we did a base workup, and you would isolate in the acetal. So this would be your final product. So these two are in equilibrium in acidic conditions. So that is your answer for that one. Okay, this next one is a multi-step reaction. You did not have to do the mechanism for this first one. Any R group that's not tertiary with KMNO4 in these conditions, heat with base followed by an acid or water, will give you a carboxylic acid. Just chop that off. KMNO4 just wants to do whatever it can. The next step of this reaction is you take a carboxylic acid from your step before, and it goes through SOCl2, and you don't have to know the mechanism for that one either for this semester. In future semesters you might, but as long as you know that this goes to chlorine, and then this lithium aluminum hydride. So aluminum hydride with 3 tert butyl groups, or tert butoxy groups. Let's see what it looked like. This, I think. So this whole thing is negative, and then your lithium is positive. So there's only one hydrogen. So because there's only one hydrogen, this basically acts like one equivalent of hydride. So this is a weak reducing agent. The mechanism is the same as we've seen with hydride in many other cases. We get O minus, this hydrogen is added here, and the chlorine. This comes back down and kicks out, and the carbonyl is restored. A lot of my students got that right in recitation, but it stops right here because there's not an excess of hydride, so it stops at the aldehyde. So that is similar to dibol H, it just stops at the aldehyde. Okay, and then the next one is propose a reagent that would accomplish the following transformation. So dibol H would do that. PCC would not. Let's see. NABH4, PCC is oxidizing, so that wouldn't work. NABH4 could not react with this. It can only react with aldehydes and ketones. And LAH can react with everything, but it would take it all the way back. It wouldn't just stop at one. So dibol H is one. The other one is this. This lithium triterbutoxy aluminum hydride would also work. So just a weak reducing agent would work. Okay, the next one is propose a reagent that would follow the this one is what would be the reaction of these two. My students really struggled with this, so this is a Wittig reaction, and I think it's easier to line up the heteroatoms so that it looks like this, and technically this is a Yllid, so one of these is positive and one of these is negative, but I'm not gonna make you worry about that. So these 3 R groups line up with the oxygen, and this would attack here, and this attacks here. Actually, this attacks here, and this attacks there because it's attracted to this partial positive spot. And you get what I call a box. This looks like a box where a bond has formed right here. There's a single bond still here and another bond right there. And my students actually got this right, but then they forgot to do the C6H5s here. A lot of y'all got that right. And the other thing is you just lost this other group, these other carbons. So make sure that you include those. And then we will do an additional reaction where it basically goes through the exact same steps where this bond comes here and that goes over there. And no, I did that backwards. I always do that. This comes down here and this goes up there. So you get a double bond oxygen to the phosphorus with its 3 R groups. And you get a double bond right here. And at first I draw it like this just so that it's easier to see. That looks kind of crazy. So more accurately, it would look like this. So this is the Wittig reaction. So you end up getting this. So your final answer. So my students and I apparently need to work on that mechanism. That was one that a lot of y'all missed. Both ways. We did it this way and if proposing the reagents, and you struggled both ways. Okay, so this next one is another multi-step reaction for this question. The more reactive carbonyl, the hint is the more reactive carbonyl will react with one equivalent. So if you have one equivalent of this, it's going to react with the more reactive. And what I mean by more reactive is more electrophilic, right? Because it's the positive charge that attracts the nucleophile. So both of these have a partial positive, but which one has more of a partial positive? Well, this has induction where these carbons can donate electron density from two sides, but this only gets electron density donated in from one. So this aldehyde is a lot more reactive than this ketone. We've done this mechanism quite a few times, but if we have a ketone with one equivalent, the first thing that happens when the alcohols react, this is the same exact mechanism as we did here, just with a slightly different alcohol. But the first step is our ketone gets protonated. So we get OH plus, and then our alcohol will attack here, and this will kick up. So we get OH, and then O, there's an H here, OH plus. Oh, sorry, I was off the camera. Apologies. And then we essentially get a proton transfer. This is the hemiacetal structure, where we have OH2 plus here. Oh, this is an aldehyde. I always lose my hydrogens. O and then OH here. Then this carbonyl, quote unquote, will restore and kick this leaving group out, and you get this structure. It's very weird looking. It's in resonance with another where the positive charge is fully on the carbocations. Then we attack here, and this kicks up, and you will get this. I'm going to flip this over so it's easier to see, but basically, well, I guess I don't have to. O here. This is double bonded to the O that just attacked right there. This still has a hydrogen, and it's positive, and then there's a hydrogen here. And then we would deprotonate, the last step, minus H plus to get, now I'll flip it around so you can see more easily, this structure. So that's the first step. The next step is reacting with this NH2. So this is essentially a primary amine. So this is going to make an imine. So now this is going to attack at the only available carbonyl. I'm going to draw a long arrow to up here. And you will get the O minus here, and then the NH2. So it has two hydrogens and then another NH2. So this is positively charged. And this is negatively charged. And it's in the presence of acid, but it doesn't first protonate because usually an amine will attack more quickly. But we'll deprotonate here and get, oh, I left my other side off. Oh, like this. So we deprotonate that, and it becomes NH, NH2. Now this is neutral, and we have OH here, and then over here we have our whole big group. And now the acid will come into play, where then we'll protonate this group, and you get NH, NH2, OH2 plus, and over here you have your whole big structure. This is a protecting group, so this one is not going to come into play right now. Then your lone pair from your amine will come here and kick this out, and you will get, when you add the acid in also, this is a reversible reaction. So when you add the acid, you get your NH2, H plus, and then over here we've now restored our aldehyde because acid makes this reaction reversible. And then you get a deprotonation step. So your final step is this amine NH2 and, oops, sorry, there's a nitrogen there. I'll redraw this where it's not on the text. So B is in NH2, and then you have your aldehyde here. Now then if you reacted that, question 10 with KOH and H2O, you don't have to know this mechanism, but it basically will get rid of this imine, so you end up with just an aldehyde. So that is the multi-step reaction 8 through 10. And 11. So now we're taking this and we're reacting with MCPBA. This is a Baeyer-Villiger oxidation. Baeyer-Villiger oxidation. And so it's going to preferentially migrate different things, but it migrates hydrogen first. So be sure that you know the order that it migrates. I believe it's like hydrogen, then tertiary. I don't know where phenyl is, but hydrogen comes before tertiary, then secondary, then primary. So it's not intuitive. So you don't need to know the mechanism, but you do need to know the order of migration here to get this carboxylic acid. So we went from an aldehyde to a carboxylic acid. And then question 12 asks, what's another reagent that would have accomplished the same transformation above? And so another reagent that would accomplish that is an oxidizing agent. So Jones reagent, or let's see, KMNO4 would have accomplished that. So any oxidizing agent would do that. Take you from an aldehyde to a carboxylic acid. Okay, this next one's kind of a trick. I had intended for this to have one hydrogen on it, and I forgot to draw it in. And then it became a tricky question because we only learned how primary and secondary amines react. You have to be able to deprotonate. So this being a tertiary amine, it would not react. So the answer to this is no reaction. This one is very similar to the reaction we just did on the last page. The amine attacks and kicks up, and you get O minus and NH plus with its CH3 still there. Then this would deprotonate or proton transfer to give you OH and H with this, and that's neutral. And then in the presence of acid, then this would protonate again. And so we get OH2 plus with NH. And so this carbonyl, quote unquote, restores and kicks this out, and you get a double bond to a nitrogen with, it's still bonded to that hydrogen. So because of the formal charge, it's positively charged there. If you're not sure why, look that up. Plus the water that got kicked out. And then we would do a deprotonation step to get your overall, I turned that into an ethyl, but it was just a methyl. I did that here too. It's just one thing off of it. I don't know why I did that. But your overall final product looks like this. So you basically just took this in CH3 and lost these two hydrogens to make a double bond to the nitrogen there. Okay, this one actually my students did pretty well on. The first step in this is exactly the same mechanism as we did here and on the first page here. Question 2. So my students did pretty well here. So the first step is, of course, protonation, OH, and that's positively charged. And then there's no nucleophile, so this oxygen will act as a nucleophile and kick that up. And we get, let's see, I like to number. So if this is carbon 1, 2, 3, 4, 5, OH. And then this oxygen, this is 1, 2, 3, 4, 5. And so the oxygen forms a bond, like a bridge sort of, between carbon 5 and carbon 1. When that bond forms, it's still positively charged. And that's a big thing I saw people struggling with today in recitation is, oh, and it also still has this methyl group on it right here. This carbon has a methyl A in that. Is they would not know when to protonate things. So it's oxygen right here. So be sure that you're on top of where your proton is. It doesn't 100% matter at what stage you maybe like add the acid in. Oh, sorry. Oh no, all that was off camera. Okay, so basically, this gets protonated and then the alcohol attacks itself and you get a 6-membered ring with oxygen in one of them. Make sure to count your carbons here. But one of the biggest things I saw my students struggling with is like forgetting to put positive charged things whenever they gained or lost protons. So a lot of times, like with alcohols and aldehydes or ketones, the protonation happened first. With amines, the protonation happens second. I won't ding you too much on when you protonate, but I will ding you on not having the formal charge where it's supposed to be. So if you're not sure on that, you can go back and rewatch the video. So normally, if it's not a cyclical hemiacetal, it would keep reacting, but when it can only react with itself, there's nowhere else to go, so it stops right here. Okay, this one is going from a primary alcohol to an aldehyde. So we need a weak oxidizing agent. And so diol H should do that. Or, oh wait, I don't know why I was thinking that. PCC will do that. That's it. Diol H is a reducing agent. PCC is the only one that is a weak enough oxidizing agent to stop right there. Okay, this is another one my students really struggled with. If we want to replace this with a carbon, we use a Wittig reagent. So we've already had one like this, C6H5, 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 and then double bonded to whatever we want it to go there. So we need 2 carbons there. So I always just draw the double bond to whatever I want to end up right there to get this question. Propose the reagents for the following transformation. Okay, you don't need to show the mechanism, but the first thing is this is an imine. And to get an imine, we react a primary amine with a carbonyl, right? Some kind of carbonyl. Actually, to get this exact imine, is different. It is on a ring, but to get this exact imine, we already saw a product or a molecule like that. So we first need to oxidize to get to this, and then we can do our amine. So we need to go from our secondary alcohol to our ketone and then react it with a primary amine. So the first step, any oxidizing reagent will work because it's a secondary alcohol. So secondary alcohols will go, they can only be oxidized one time. So PCC or anything else, Jones, KMNO4 will get to this. And then after you have this, you can react with acid and your amine, which should be NH2, CH3, I'm just going to draw it in with a CH3 and 2 hydrogens. So that should be your reagents that you need for this one. Okay, and then for the last page, we have a multi-step reaction. This is for question 7, but for 19. So the first step is, this is actually, you did this exact thing in your lab. So first step is electrophilic aromatic substitution, which I know because we have an aromatic ring, a Lewis acid, and a halogen. And the only reaction that we learned on aromatic rings was electrophilic aromatic substitution. Put that in the presence of magnesium, and you get a Grignard reagent. And so that is the equivalent essentially of this. And then if you have carbon dioxide, this will attack your carbonyl carbon, just like you've seen over and over, and this bond will break. And you get your benzene bonded to a carbon, double bonded to an oxygen with O minus. There's nothing that it can restore to kick out, so I believe you should add acid, which I didn't have. So if you'd stopped here, I would have given you points. But if you add acid to do a proper workup, you will get this benzoic acid, which you saw this happen in your lab. You added benzene. You might have had bromobenzene with magnesium to get your Grignard reagent, and then you poured your Grignard reagent over dry ice. You had a reaction, added acid, so that a little white precipitate would come out, because this is not soluble in water, I believe. So I think that's what you did for your lab. So that is your one way that you can make a carboxylic acid. So hopefully this was helpful to y'all, and good luck studying.